Here, we look at the math behind an animation like this one, what's known as a complex Fourier series. Each little vector is rotating at some constant integer frequency, and when you add them together, tip to tail, the final tip draws out some shape over time. By tweaking the initial size and angle of each vector, we can make it draw pretty much anything that we want. And here, you'll see how. Before diving into it all, I want you to take a moment to just linger on how striking this is. This particular animation has 300 rotating arrows in total. Go full screen for this if you can. The intricacy is worth it. Think about this. The action of each individual arrow is perhaps the simplest thing you could imagine, rotation at a steady rate. And yet the collection of all added together is anything but simple, and the mind-boggling complexity is put into an even sharper focus the farther we zoom in, revealing the contributions of the littlest, quickest, and downright frenetic arrows. When you consider the chaotic frenzy that you're looking at, and the clockwork rigidity underlying all the motions, it's bizarre how the swarm acts with a kind of coordination to trace out some very specific shape. And unlike much of the emergent complexity you find elsewhere in nature, this is something that we have the math to describe and to control completely. Just by tuning the starting conditions, nothing more, we can make this swarm conspire in all of the right ways to draw anything that you want, provided that you have enough little arrows. What's even crazier is that the ultimate formula for all of this is incredibly short. Now often, Fourier series are described in terms of something that looks a little different, functions of real numbers being broken down as a sum of sine waves. That turns out to be a special case of this more general rotating vector phenomenon that we'll build up to, but it's where Fourier himself started, and there's good reason for us to start the story there as well. Technically, this is the third video